Hi everyone, and welcome to our lecture video today talking about photoelectron spectroscopy. And by the end of this video, you will be able to explain the relationship between the photoelectron spectrum and the electron configuration of an atom or an ion. So to get us started, we want to first introduce the photoelectric effect, which we can break down: photo meaning light, electric meaning electron effect. So it's the effect of light on electrons. And we know from our previous knowledge in our previous classes that light exhibits particle-like properties. And those particles are called photons. And photons, given that they have a specific wavelength, they also have a specific energy associated with them. And that energy is therefore quantized, meaning there's a finite and definite value. We can describe that the energy of that light, or EMR as our abbreviation, is proportional to its frequency, aka its color. So we know, right, that the energy of a photon, E, is equal to h nu. So if I increase my frequency, I'm also increasing my energy as well, which means red light, which is lower in frequency, is lower in energy, and violet light, which is higher and has a higher frequency, is also going to have a higher energy. And that affects electrons differently. So what we have here are three examples. We have red light shining onto a metal sample. This sheet right here, we can think of it as a metal sheet, like a sheet of aluminum, like aluminum foil. Our second example is shining green light. So it's the frequency associated with green light. And our third example is blue or violet light. What we know, red light is the lowest in energy. So when I shine red light onto this metal sheet, nothing happens because the energy in red light is not sufficient enough to actually eject electrons. However, as we start to increase our energy, green light has more energy than red light. So when we shine green light onto a metal sheet, there's enough energy provided for an electron to be completely ejected from our system. Similarly, as I increase my energy one more time and I shine blue or violet light onto my metal sheet, ultimately we eject more electrons. Each of those electrons are going to have a higher energy associated with them as well. And this is called the photoelectric effect. There's a light effect on electrons, and if we shine a high enough energy frequency of light onto some sort of atom sample, enough energy is provided potentially to eject electrons. And in fact, this is what won Albert Einstein the Nobel Prize back in 1921. So we can utilize this knowledge that if we shine light with a high enough energy, electrons are ejected. That's going to come in handy when we talk about our specific photoelectron spectrum today. So our next piece of some potentially reviewing information is Coulomb's law. And Coulomb's law evaluates the electrostatic force of attraction or repulsion between two point charges. Going through this, F here is the electrostatic force. K is Coulomb's constant. Q1 and Q2 are each point charges, and I'll explain more what that means in a moment. And R is our radius. And it's our radius squared in the denominator. So all this is saying is that two positive charges, two negative charges, or a positive and a negative charge have some sort of electrostatic force. The opposite charges, that force is attraction. The same charges, that force is repulsion. And what we see here is our inverse square law. Our inverse square law says that the closer the distance, the stronger the force. If I decrease the radius between my two charges, ultimately that's going to have a larger electrostatic force. So now let me pose to you a question that you can reflect on before moving forward. Based off of our two examples, which negatively charged electrons would be more strongly attracted to positively charged nucleus? Would electrons closer to the nucleus have a more strongly attractive force? Or would electrons further away have a more strongly attractive force with the positive nucleus? So the correct answer here is that electrons closer to the nucleus are going to have a stronger attraction. So if we think about this, if this positive charge here is my nucleus, and we have a negative charge to the left, this is a -1 charge and a +1 charge. There's some sort of attractive force here. If we move those further away from each other, like they're magnets, the further apart you pull magnets, they're not going to feel as attracted to each other because the distance is so far. So even though we have the same point charges, even though Q1 and Q2 are the same, we can call Q1 -1 and Q2 +1. There's no sort of attractive force anymore when they're further apart. So the closer these point charges are to each other, the more strong their interactions are. And that comes in handy because that's what binds together our atom. In an atom, there's an energy that describes, we call it the binding energy, that describes the energy that holds together our atoms. And the energy that holds together our atoms is associated with the energy of our electrons and the energy of our protons in our nucleus. It's the attractive forces between our negatively charged electron. So we can say that Q1 is going to be -1. And our positively charged nucleus, if we have one proton, we can call this +1. And what happens, right, and we just talked about this on an energy level when we talked about the Bohr model, the lower the energy level, the closer that electron is to the nucleus. And as such, it's going to have a stronger attractive force that holds those together.